Hello again, kids. We're back to the third problem on your notes. It is about a train. God, it always comes back to the train, doesn't it? So we've got a train, and it's traveling at a rate of 0.8 kilometers per minute along a long straight track moving in the direction shown below. So you see the train. I know my picture's not beautiful, but the train's going along this track. So the train and the direction it's going is represented by X. Alright, and then a movie camera 0.5 kilometers away from the track. So that camera is actually at a constant distance from the track, right? The only thing that's constant in this problem is this 0.5. That camera's not moving, it's 0.5 away from the track, alright? And it's focused on the train. So if you can imagine, this camera is sort of moving in this direction. As the train moves, you've got to turn with the camera so that you can see the train. All right, you can't just hold the camera still because the train will go by and you won't be able to see the train anymore. All right, so as we move forward in this problem, what's changing is the X and the D. Alright, the distance from the camera to the train. The other thing that's changing is this angle here, which we'll call theta. Alright, those are the three things that will change as the train goes by. The camera angle, the distance from the camera to the train, and the distance that the train has actually traveled since it's passed the camera. Alright, so first thing we want to do is express D, the distance between the camera and the train, as a function of X. Well, this is a known geometric formula. Since this is a right triangle we've created here, basically all we have is the Pythagorean theorem. Now hold on, little Mary really doesn't want to be asleep during this lesson, so it's been a struggle. Okay, hang out, Mary. I'll wait till you holler. Alright, so we got D is, of course, the hypotenuse. So this is going to be D squared equals X squared plus 0.5 squared. All right, so that's the formula that relates everything, okay? And as D changes, X will change. All right, so that's your first formula. You can solve that for D, or you can leave it like this. It's actually going to be easier to take the derivative of this if we leave it in this form. We don't want to have to deal with a radical. We'll just do an implicit derivative. So I'm going to leave this as D squared equals X squared plus 0.25, and that will make life much, much easier. So now the next thing we're going to do is look at our information. All right, the rate at which the train is traveling is 0.8 kilometers per minute. So what is that? Well, that gives me how fast the train is going. And the train, remember, is X, so it's dx dt equals 0.8 kilometers per minute. All right, so let me slide that over. And then the next thing is a movie camera 0.5 kilometers away from the track is focused on the train. Alright, so that's really all we have. Dx dt equals 0.8 kilometers per minute. Now, let's look at our snapshot in time. Part B says, how fast is the distance from the camera to the train changing? So they're asking about this now. How fast? Alright, so they're asking, what is dd dt? How fast is that distance changing when that's at this moment in time when the train is 1 kilometer from the camera? Now the train to the camera is represented by D. So when D equals 1. Does D always equal 1? No. This is at the moment in time, at the snapshot in time when D equals 1, we want to know what is d dt. d dt is always changing. D is always changing. You cannot just plug D in there, all right? You have to wait until the very end of the problem before you plug in d equals 1. You've got to take a derivative first. That's always your rule of thumb on these problems. Take a derivative of a formula first, then plug in values. Okay? So, how do we find d dt? Well, luckily we have this lovely formula over here. So we say we're going to take the derivative of that formula. 2d dd dt equals 2x dx dt plus 0, right? Because the derivative of this 0.25 ends up being 0. So you've got 2d dd dt equals 2x dx dt, and now all we do is we plug them in. Now we have what is d is equal to 1. Can we figure out what x is at this moment in time? Well, yes, we can. We don't want to do it until this point, though. We don't want to do it ahead of time because we might be confused. But now we need x, right? You need x. So let's figure out what x is using our formula from our triangle. So 0.5 squared plus x squared equals 1 squared. Because we know d is 1, right? We know what our formula is for our triangle. We know the formula for the triangle is 0.5 squared plus x squared equals d squared. Right? What terrible writing I'm getting on this tablet today. So all we're going to do is plug in there and solve for x. So we get x squared equals 0.75, and then x equals radical 0.75. So radical 0.75 is what we're going to put in for x. We know what we're going to put in for d already. We've got d, we've got x, and guess what? We even have dx dt from up here, up above. So we have everything except for d dt, which is exactly what we need. All right, so before we even get started on this, what we could do is we could divide the whole equation by what? 2. So let's do that first. So we get d times dd dt equals x times dx dt. Now we'll plug them in. So d is equal to 1. dd dt is what we're trying to find. X is equal to radical 0.75. And of course, let's see here. Let's see here. 0.8 is dx dt from up above. So we're just plugging in our values, right? X is radical 0.75. If you look up above, it says dx dt is 0.8. So now we're done, basically. So we get dd dt. When you need to round here, just round to the nearest hundredth, kids. So I'm going to round, and I get 0.69 kilometers is our unit of distance, and then minutes is our unit of time. So it's kilometers per minute. So that one's done. Now, the next one might be a little trickier for some because it involves a trig function. Sometimes we have a hard time remembering our trig functions. So in this one, what we're going to do is we're going to find how fast is the camera rotating. So that has to do with theta and the speed of theta, the speed of the change in theta. So we're going to find d theta dt. But in order to do that, we need to go ahead and write a relationship between theta and everything else. Well, a simple relationship between theta and d, which would be the handiest one because you know the train is 1 kilometers from the camera, gives you d. All right, so part C, we're going to find what is d theta dt when d equals 1. Well, what is something we could use to find a relationship between theta and d? Well, we have the adjacent side to theta, pardon me kids, is 0.5, and then d is the hypotenuse, right? So which trig function relates adjacent and hypotenuse? Well, that would be cosine. So we're going to say cosine theta equals the adjacent side, which is 0.5, over the hypotenuse, which is d. So now simplifying this a bit, oops, my computer is doing very strange things right now, kids. I think it's gagging on all the stuff I'm putting inside of it. So first, all I need to do now is take a derivative. Okay, so I'm going to say, what's the derivative of cosine? Good review. Negative sine theta d theta dt is equal to, now this is 0.5 d to the negative 1, right? So if I take its derivative, I get negative 0.5 d to the negative 2 dd dt. Well, we have dd dt from the previous problem. We know what d is. We know we can find negative sine theta as well. So we're going to be fine here. All we have to do is figure all this stuff out. Okay, so first of all, let's go ahead and find negative sine theta. Remember, we filled in all the sides at this snapshot in time, right? We know that d at the snapshot in time is 1, and x is radical 0.75. That's from the previous part of the problem. So sine theta would be opposite over hypotenuse, so that would be radical 0.75 over 1. All right, so we have negative sine theta is equal to negative radical 0.75 over 1 times d theta dt, which is what we're trying to find, is equal to 0.5 d to the negative 2. Well, d is 1, so it's 1 to the negative 2. And 1 to any power is 1, so that's not going to do much to the problem. And then times d dt, which I'm going to leave that not as 0.69, but instead as 0.8 times radical 0.75, because it just is going to turn out much tidier. So we'll use the radical form of d dt that we had from the prior part. So it's times 0.8 times radical 0.75 from the part B of the problem. Now, here's the deal. If you divide both sides by radical 0.75, what you end up with is, actually let's divide by negative radical 0.75. We get d theta dt equals 0.5 times 0.8. Oh, negative 0.5 times 0.8. So, negative 0.5 times 0.8 is equal to d theta dt is going to be whoa, wait a minute. I did something here. Oh, the negatives cancel on both sides. It is not negative 0.5. It's just positive 0.5 because the negative 0.5 is here from before. So you have negatives on both sides. So this just turns out to be 0.4. Sorry, kids. Radians is the unit of theta per minute. You can always look at the units of the unit of the d theta. The unit of theta is radians. The unit of time is minutes. So it will always work out that way. So that's kind of a nice double check. So that's that one. And you can look back over that problem with Ms. Haney again if it helps. That I know is a tough one. Let's go on to the one about the spherical cell. Hi, sweet pea. What are you doing? Oh, gosh, gosh, gosh. I'm sorry. I'm sorry. I'm almost done. Not really, but kind of. So, let me look at how far in we are here. 15 minutes again already. Wow, that was a long problem. So, I'm going to move on to the next problem, which is about a spherical cell growing at a constant rate. Okay, so here we have a spherical cell growing at a constant rate of 400 mu meters cubed per day. At what rate is its radius increasing when the radius is 10 mu meters? Now, that's a new letter for you. It's a Greek letter, mu, not a big deal. It looks like a funky M. So let's go ahead. First thing you need to know is the volume of a sphere formula, because this is a unit of volume. Okay, so you're given a unit of volume, so you need a volume formula for your sphere. So V equals 4/3 pi r cubed is the formula for the volume of a sphere. What we know and what we're trying to figure out, we're trying to find dr, the radius increasing rate, dt. When r is equal to 10 mu meters. And then the last thing you need to know is that you need that rate of growth. Okay, so 400 mu meters cubed per day. Well, mu meters cubed is volume, right? So it's going to be, this is dV dt is equal to 400 mu meters cubed per day. That is the rate that you are given. So this is actually not terribly hard compared to what we just did. It's a walk in the park. So all we have to do here is go ahead and take a derivative. So take the derivative of the left side, we get dV dt equals, take the derivative of the right side, we get 4 pi r squared dr dt. And then all we need to do is plug in what we have and solve for dr dt. So dV dt is 400. We have that. 4 pi. R is equal to 10, so it's 10 squared. And then dr dt. Now we're going to divide both sides. See, what we get on the left side is actually going to be 400 pi. So I have 400 equals 400 pi. I think I said the left side, I meant the right side. Dr dt. And then we divide both sides by 400 pi. And our final answer is dr dt equals 1 over pi mu meters, because radius is in the terms of mu meters, and then it's per day. I think I have to pause again for a second, make somebody happy, and then come back. So there might be a little gap. Alright, so water is flowing at a rate of 50 meters cubed per minute from a shallow concrete conical reservoir, say that 3 times fast, of base radius 45 and height 6. Alright, so first thing is, you've been given the radius, you've been given the height, you need to find a relationship on this cone between the radius and the height. So this is what the cone looks like. Well, it's a pretty poor example of a cone, but it's the best your math teacher can do. And you have your radius and your height. Okay, so the base radius of the cone at this point is, what does it say? Base radius 45. meters and the height is 6 meters. So this obviously is not to scale. Now, what you can do is you can always find a relationship between the radius and the height of the cone if you're given a base radius and an overall height, because you can use similar triangles. Okay, so I'm going to pull this little right triangle here out of my cone. See it? See the right triangle? I'm going to pull that out, and I'm going to get an overall relationship between my radius and the height, no matter what the water level is in the cone. Because this is 45, this is 6. If I were to draw a radius at some point in time and a height at some point in time, okay, what I could do is I could say that the radius over the height equals the radius over the height. Okay, so remember this, I don't have that height in a good spot, so let me see. This whole side, okay, is 6. This whole height is 6. So we're going to do 45 over 6 equals r over h. Okay, so we say 45 over 6 equals r over h. Now this is very simple geometry problem. This is why you have to take all these other classes before you take calculus, is because you use it all. Eventually it all gets used. And because you are all mathematical wizards, of course, you remember all this stuff. So we do, we go ahead and we divide out to figure out what r is in terms of h. So if you cross multiply and divide, or basically just multiply both sides by h, you get 7.5 h equals r. Because 45 divided by 6 is 7.5, and then you just multiply both sides by h to get rid of the h on this side. So there is your formula that gives you r in terms of h. You're going to need that for this problem. Alright, you're also going to need the volume formula for a cone. Alright, so a couple different things you'll need to know. So part A asks the following: how fast in centimeters per minute is the water level falling when the water is 5 meters deep? So remember, nothing is constant, right? Our water is falling. We're looking for a snapshot in time when the water is 5 meters deep. The depth of the water is h. So what it's asking for is centimeters per minute. So how fast in centimeters per minute is the water level falling? So water level is h. So you're finding dh dt when h equals 5. When h equals 5, we can easily figure out what r is, so we'll do that at some point in time. We could do it now, we could do it later, but let's wait till later because we want to resist the urge of doing something like plugging in all the variables, right? We don't want to plug in the plain variables until after we've taken a derivative. That is the most important part of doing a related rates problem. So we are going to use the volume formula now because we know what dV dt is. See, it gives it to us here, 50 meters cubed per minute. So dV dt equals 50 meters cubed per minute. Alright, so let's go ahead and use our volume formula. Alright, so what we have is V equals 1/3 pi r squared h. That's the volume of a cone. Now, we don't want r's in our problem. We don't have any r's. We don't want two variables. We don't want to have to do a product rule. So what we're going to do is we're going to plug in. We know that r equals 7.5h. We would prefer to just have one variable on either side. So we say v equals 1/3 pi times 7.5h squared times h. Alright, so now square it, simplify it, make it pretty, and what we get is v equals 18.75 pi h cubed. So now we can take a derivative. So when we take the derivative of this little bugger, we get dv dt equals 3 times 18.75 is 56.25 pi h squared dh dt. Now we can find dh dt because we know h and we know dv dt, so we're going to be all good. All right, so let's go ahead and plug everything in. So dv dt is 50. That's equal to 56.25 pi h squared, right? Remember, when you square something, you have to square both parts. Like up here, that's 7.5. When we squared it, we square the h and the 7.5, right? Because it's a product. If it were a sum, you wouldn't do it that way. You would do double distributive property. But when you square a product, you bring that squared in on both pieces. All right, so then I got 5 squared, and then I got dh dt. I sort of got off on a tangent there. Now we just divide by everything that is not dh dt, and we get 0.0113 meters per minute is equal to dh dt. Okay, all I did was divide by all of this stuff over here. I want to save some time, so I don't want to have to write that down. All right, so now what we get finally is, it's easier to do this in terms of centimeters, 1.13 centimeters per minute equals dh dt. So that's the answer to part A of our problem. Part B is much simpler because it just asks us, how fast is the radius of the water's surface changing when the water is 5 meters deep? And my computer is just dragging right now. I can't get it to move. Very, very slow. I don't even know what page I'm on now. So I can't go up to the problem because the computer is being very glitchy, so I'm just going to continue with part, well, maybe, I don't know, it's going to move on its own now. There we go. Part B, the last part, says how fast is the radius of the water's surface changing when the water is 5 meters deep. So all you have to do here, you already have a relationship, R equals 7.5 h, and all you're talking about is the radius and the height of the water. So that's the formula you want. You want something that relates the radius to the height of the water. So now we take a derivative, we get dr dt equals 7.5 dh dt. And then we go ahead and plug in what we are just found dh dt to be, which was 1.13. So we get dr dt equals 7.5 times 1.13, or dr dt equals 8.48 centimeters per minute. These notes are on my website. I think they're much tidier on my website because the computer was not quite as glitchy when I did them last year. They may not look identical, but pretty darn close to what this does. If I went too fast at any point in time. So your homework on this, I do not have in front of me right now. That is very strange. I'm hoping Miss Haney has the homework on this. If not, I will have to find it for you. That is very strange. So I'm going to pause again and see if I can find it. Okay, so I found it. Your homework is page 158 to 159, 1 through 23, odd, and 28. And then you'll have more homework on this next class. It'll be a worksheet, but this class, it's bookwork. And most of the answers are on my website. If you need a hint, go to the website for the hint. These are difficult problems, so you will likely need some hints. Good luck, and have a great day.